Hello and welcome to watching this video. This will cover chapter 1 of the Network Plus certification book. This is for the CTS-1134 class. This chapter describes the difference between a peer-to-peer and a client-to-server networks, as well as some of the protocols used in a network. And we'll jump into also describing what's the physical topologies, so different type of topologies that you can have on a network. Point 4 is one of the most important, the 7-layer OSI model, which actually rules the TCP/IP stack protocol. And that describes how everything communicates on a network. That's one of the prime bases of networking. And also at the end of the chapter, it goes a little bit into some of the safety on networking and also some troubleshooting issues. All right, so when we talk about a network, there's a topology. Topology is what describes how the network is composed together, right? So you can describe it two ways. You can describe it through a physical topology or the logical topology. Physical topology means all the physical connections, how every device is interconnected with each other, either through a wire, through fiber, through a wireless communication, or any other communication that you can have there. So it will describe every single connection between one to the next and to the next and to the next, how that whole chain goes out on the network. Logical topology, and on the other hand, is more as how things are actually working through the software. If you're on your computer and you go to google.com, your computer connects directly to Google and you get your page. So logically, you're connected directly to Google and you're downloading information, you're sending information, and you're establishing that communication between your computer and Google. That's logically you're connected there. Physically, you're not. Physically, you connect to your home router. The home router connects to your provider router, either Comcast, AT&T, Verizon, any other provider that you might have at home. And that provider will connect to a larger ISP provider in your city, in your town. In our case, will be in Miami, and Miami will connect to. I think the next hop is in Atlanta, Georgia, and from then on, it goes somewhere when it needs to find where Google is connected to. So physically, you're connected to your home router, to your AT&T or a Comcast provider. That provider connects to somebody else, and so on until you get to the end point where you're actually getting your information. Logically, you connect directly to your endpoint, in this case, Google. To all of this to operate, you need a network operating system, right? A network operating system is like the word says, is an operating system that it sets up all the rules and all the protocols and it handles everything in order to make the communication to work. All right, so let's jump into some of the terms. A peer-to-peer network, or P2P network model, is when you have computers connected to each other. It's peer-to-peer. There is no centralized network. There's nothing controlling your network. It's just connection directly from one device to another, and you're isolated on your own network, right? And all those members of that network are either those computers are either called nodes or hosts. You'll hear that term back and forth. Is a node or a host, right? So each computer, it has its own administration, resources, security. It's just like all individual devices, right? The advantage is they're simple configuration. You can connect back-to-back devices and they will talk to each other. You just basically throw a cable and they will work. Now, is it optimal? Well, no, because they're not scalable. You have a network of 2, 3, 4 computers, that'll be okay. But if you have a network with 100 computers or even 50 clients or 20 clients, if you try to do this peer-to-peer, it's connecting one to each other. So you're going to have this basically spaghetti of cable. So it's not practical at all. And on the next one, you'll see a description of how it's done. And here it is. So on a peer-to-peer, you see that, for example, on the upper left, the Ubuntu desktop has a wire connected directly to the Windows machine, and another to the Mac OS machine, and another one to the printer. Now, in order to have that done, you'll see that you will require your Ubuntu desktop to have 3 network cards. So is your Windows 10. So is your printer. I haven't seen a printer with 3 network cards, but in this type of peer-to-peer model, you'll have you need to have that physical connection so you can connect everything all together. On this one, they show like a scanner that is being shared by the Mac OS machine or host. So that node has the scanner, and that's how it can be shared. The printer is directly connected to your network, so it requires, like I said, a connection to every single device. But this is more what is called like a mesh connection. Mesh meaning that everything is meshed together. Everything is connected to everything. Yeah, as you can see, this is very, very practical. When you have like, this is only three hosts, but when you have 20, then it just is, it's just not practical at all. Now, on the client to server model, that's a different story, because here you have some machine that is centralized to controlling all your devices, and controlling who goes in and who has access or not access to your network. One of the good examples is the Windows domain, right? That has a Windows server that controls everything. Windows has what's called the Active Directory. For those who are not familiar with Active Directory, is a centralized database that it contains all the accounts for all the clients on your network, or the different computers. Not only the computers themselves, the physical devices, but also accounts for the users, and also devices like your shared devices, like your printer or storage or anything like that. So everything is centralized on Active Directory. So Active Directory complies what is it will do a Active Directory domain services. So that's your domain controller. Your domain is all those collection of users on your network. Okay. Now on this model, each computer is called a client, because now you're not hosting. On the other description, you saw there was either a node or a host, but here each single computer on your network is considered a client. And see, this looks much, much better. You have your domain controller with Active Directory, right? It has your domain database, and there all your clients connect to that domain controller to be accepted into the network and be allowed to be talking to everything on your network. So you have your Mac OS, your printer. So your printer is now centralized to your domain controller. And when any of the other clients needs to use it, it can use it through the domain controller, or the domain controller will give you access to be able to access that printer. So like I said, see, it's a little bit more, is a much more cleaner, topology. So yeah, that domain controller handles a lot of information, and it will manage your clients and the resources. It will ensure access and control the access for those users, right? They can control where files you can access, which software you can access. It can restrict the network access. It said a user can have a limited amount of resource allocated to that user, or a power user can have more resources and more services available for them, right? Um, so of course, when you have something like this, a server like in this kind, it requires a network operating system for that. In this case, the example is with Windows server, and that will require more memory, more processing power, more storage capacity, and you will have some special hardware in order to have all these, processes done. But definitely you'll need a much larger computer, a server in this case, to work as a domain controller, or multiple ones. Some large enterprises like the Miami-Dade College, it will have multiple domain controllers across multiple campuses, and they'll talk to each other and they'll back up each other in order to be able to handle the number of accounts that are out there. I think right now, or used to be, that the college had at least 18,000 registered users on their database. I'm not talking about a other machines that are registered there, or the services registered there. I'm just talking about clients, users registered on the database. Now, this NOS on the client server applications will provide some network services and some resources for your users. It could be application databases, any kind of information that is available for you on your enterprise. And it might point also to other computers, to other servers to get additional information. For example, if you have a company, then you'll have your may have your accounting server, and then you have your inventory server that handles different information for different departments. So the inventory is on one server, and your accounting is on another server. So you keep your data separated, but yet the operating system allows these applications to be able to talk to each other. So when the salesperson or an accounting wants to do a sale, they can take a look at the inventory and see how much is the inventory, and the same. Likewise, the inventory people can come and say, let's see, what orders are coming in for the inventory that I have. Even though it's in two separate servers, the operating system is the one that allows this communication to happen, and to whom is going to allow to be able to access that information. So here on a larger scale, you'll see a client accessing a web server. This is, of course, is over the internet, and you just go and access that web server. The web server has some content for you that will deliver that whatever content you require. If it's cengage.com, it will give you that. If it's mdc.edu, it will give you that information. If you go mdc.edu/personnel phone book, it will give you all that phone book information. Depends what you're looking for. It will provide that information. It is a client server application. I mean, the web server, because it's serving information to the clients, right? So now let's talk about network services and protocols. So what's a protocol? Protocol is just a set of rules, right? Any protocol, um, protocol between, I don't know, international relations between countries is a protocol, how you have to communicate with each other. So in networking, you have a protocol that is the one that defines the rules on how this communication needs to happen, or what is required for this communication to happen. So there's two primary protocols in networking. You got TCP, Transmission Control Protocol, and also you have IP, which is Internet Protocol. That's why in many books and many documentations that you might read, you will see that it's called TCP/IP, because you need to have all those the two protocols combined together in order to provide a secure network communication. So, and we'll talk about each one of them. But yeah, you have your TCP, Transmission Control Protocol, and your Internet Protocol, which is your IP. Also, some of the popular server applications that you might already be familiar with on the internet. You got web services, you got email services, DNS that you're using constantly, FTP services for file transfer, and also database services. Anything you access on Amazon when you're looking for a device, I mean, an article that you're looking for, you'll hit some database to give you all that information. And also you can have remote access services, which is to remote access some other devices over the internet. Now, I'm throwing this already in here that web services, they use TCP, and TCPs are usually assigned with a specific port. There's a range of ports we'll see later on. That's called the well-known ports, and the well-known ports are the one that already specify for specific things. A good example, it's an analogy, is that, for example, if you want to watch news, or you go to one of your CBS channels, or your CNN channel, or your Fox channel, whichever news channel you want to watch, you tune to one of those. If you want to watch sports, you go to ESPN. If you want to watch the weather, you go to the weather channel, right? And each provider, in this case, if you are using, let's say, Comcast, it will allocate a specific channel number for that service, right? So if you want to watch the weather, or get information on the weather, you will tune to the weather channel. I don't know, let's say it's channel 220. So if you want to watch the weather, I tune to 220. Now, if I want to watch sports, and ESPN happens to be on my channel 100, then I have to switch to 100. Now, what happens if I need to listen to the weather and I tune to channel 100? Well, no, 100 is used for ISPN, and all I'm going to get is the sports. I can sit there the whole day, the whole week, the whole month, and I will never get a weather report on the ESPN channel because it's for sports. So in TCP/IP, you have certain ports already allocated for that. In this case, the web services, if it's unencrypted, you'll use port 80. If it's encrypted, HTTPS for secure, it uses port 443. Email services, they use either 25 or 587, and sometimes they use TCP port 2525. DNS services 53 or 443 if it's a encrypted DNS. FTP uses uh, 21. If it's secure, FTP is 22, and so on. The ports are there. So what I'm saying is that you have to keep in mind that all those services are provided on a specific port, and you need to communicate through that port in a way tuned to that one specific channel. I cannot go and ask channel 100, I said it was ESPN, for weather when weather is on 220. I will never get that information. So if I need to get DNS, I have to use TCP port 53, which is a little tuning number that I need to use on my TCP/IP communication in order to get that information. We'll get more into that, but I just wanted to throw this all at the beginning so you understand, we'll start to catch up on what all of this is all about. And here's a little example of that. If I want to start using email services, well, email services, when you send something, you send it through SMTP. Simple Mail Transfer Protocol. So SMTP is a protocol that everybody needs to use. Protocol, remember, is a set of rules. So it has a set of rules, the way that is constructed, the way that is built, that message, how it's sent to the server is through SMTP and using that SMTP protocol. Now, when that goes to your sender's email, in my case, if I'm going to send it from Miami-Dade, I'll send it to Miami-Dade server. Let's say you have your account on Google, so the Miami-Dade would actually relay that message to the Google servers, and then you log in with your Google account and you read that email. Now, to read that email, there are two protocols to read. You can use POP3 or you can use IMAP. POP3 is a protocol that actually takes the message downloaded to your computer and it will raise it from the server. And the IMAP is a mapping protocol that it would actually go into the server, map it for your computer. Your email stays on the server, but you can still read it from your client computer. So see how the communication here is different. So SMTP is to send. So I send that to my server. That sender will relay that to the receiver email server. And then me as a client, as the receiver, I connect either through POP3 or IMAP to read the email. Because now to send the email uses one protocol, SMTP, and to read it, I use a different protocol, which is either POP3 or IMAP. So they're different protocols, different ways to send that information and different ways to retrieve that information out of the servers. All right, so let's jump right into a small LAN on a local area network. Here's a good example. You got a central switch. This is something that you may have at home. It's just like a small device with multiple ports, and then you have each computer connected on a specific port on that switch. That creates a network. That network is called a LAN, a local area network. You may have a share scanner, or you can have a share printer. You can have a network printer where everybody can access that one. The local printer, it will be shared only if that desktop allows the printer to be shared, whereas the network printer is there for everybody to reach and it goes directly into the switch. So this here is a small local area network. This is what you will see in your home network. Now, this is to describe the previous slide. You'll see that that was a local area network, right? It's usually like a small containing one space. It doesn't have to be like one room. It could be one floor. It could be one building. It depends how large your network is. But a local area network is something that is localized, something that is internal for you. The central point on that is a switch. A switch is a device that allows the communication to go in and out. So you will send and receive information across all the devices. We'll talk about more how switches work, but switches do maintain a table of who the clients are, who is connected to the switch, and is able to deliver the information to that destination. Um, we talk about topology. So for physical topology, in that case, that was a star topology. Star topology, it's meaning that you have one central device that collects all that information, distributes the information, and then all devices are connected to it. So if you see it, it looks like a star, right? So because everything goes to one central point, in this case is a switch. There are other larger star topologies, which are if all the switches connect to one central router, is also a star topology. So it's kind of like a star-star topology. Router connects to multiple switches, and the switch connects to multiple clients. Uh, each computer needs to have a network interface card or a NIC card. Actually, NIC card is kind of like a redundant term because NIC by itself is network interface card. So when you say NIC card, it's kind of like network interface card. But anyway, people call it a NIC card. Um, that's your network adapter. That's what sits on the back of your computer. The little phone. It looks like a phone jack, but it's a little bit larger than a phone jack. And you can have that on a laptop. You can have that on a desktop. The printers now come with network connections, so you will see those network cards on all the devices, right? Uh, you can have multiple switches. We'll go more in details on a larger network and when you have multiple switches. And when you have multiple switches all connected together, then you have what is called a backbone. The backbone is that central point where everything connects with each other. And let's see the next slide. Okay, so here you see you have multiple switches. You got 3 LANs. Each switch feeds a LAN. So you have one on the left with 4 computers, one in the middle with 3 computers, and one on the right with 3 computers. And they're all connected what's called the backbone. The backbone is that yellow cable that is now connecting all the 3 switches together. Now, talking about topologies, this is called a star bus topology. Why a star bus topology? Because you have a star on the left, you got a star topology in the middle, and a star topology on the right, but everything is connected together in the middle through that yellow line. That is called a bus. A bus because it has to go from one to the next to the next to the next to connect to all together. The problem with this topology here is that if you lose the switch in the middle, there goes your network. Your left side cannot talk to your right side because the middle portion is dead. If that gets taken out or gets defective, your bus gets broken and you will not have a network anymore. So that's one of the downside of the a bus topology. Normally what you would do is that you will bring a line from the end, let's say from your right side, and loop it around all the way to the left side to the other switch. So now it's not a bus topology anymore, it's a ring topology because now you set up like a ring and it's a star ring topology. And that makes it a little bit more resilient because now you can lose any of those as it's all interconnected together in a ring, then the other two will remain connected no matter how many, which one of them goes down. All right, so now that we know what a LAN is, right? A LAN is a local area network. Let's introduce the concept of a router. Router is a device that routes traffic. It manages the traffic and finds the way to find other networks. So a router is a gateway that allows you to connect 2 or more local networks together. When I say local networks, that means a LAN, right? A local area network. So you can have, let's say, within a small organization, your accounting, your sales, and your um, um, oh, inventory. I lost the word. On your inventory. And in order to communicate through all of those together, you need a router. Now, why do you want to separate that, not have it all together? Because you want all your cells to be able to talk together. You want to have the sales service within the sales area. You want the accounting to be in the accounting area with the accounting server. And then you might have some separation there, some restrictions between one and the other, right? And the same thing with your inventory. You want your inventory people to have access only to the inventory and not be able to talk too much with the sales or the accounting area. So you can have all these 3 different LANs. Three different local area networks. Now, in the old days, the routers were called bridges. So, which made more sense because now if you go from one LAN to another LAN, the only way you could do it was through a bridge that will bridge the two LANs together. Now they're called routers. But if you think about that, then now you can have a router that will connect all the things together. All right, this is more on a larger scale, but you'll see that you have A and B. A and B could be is just a home network. It connects to the internet, and B is another home network connect to the internet. And the internet, of course, it will cloud to cloud. It will talk to each other. So the router is the one that allows your local LAN to talk to the outside, right? In both cases, it's the same thing. So all devices need to physically connect to a switch. The switch physically connects to the home router, and the home router connects physically to the internet, or in this case, it will be your provider, and that provider will connect physically to somewhere to the rest of the providers, right? All the providers talk to each other. Everybody talks to each other. So the router is the one that makes that possible. He's the one that routes the traffic. When it doesn't belong to your LAN, he's the one that decides, okay, where is it going to go? And it has to go to the outside. So that outside network, it could be many names. I mean, it could be a wide area network. Uh, if you see your home router, you might see in the back of it that there's one section, mostly your 4 or 5 ports or 8 ports, whichever ports your router has, it will say LAN. And then there's one single port that's called or label WAN, WAN. The WAN is the wide area network. That's the port where you connect to your provider. So that's your WAN. Another name is also a metropolitan area network, the MAN. Which is LANs are connected in the same geographical area. You might call Miami-Dade. That's why it's also called the campus area network. Or I hear more of the campus area network than MAN, honestly. When I say into into the industry, you hear more of the campus area network. But the campus area network then will be like Miami-Dade. The Miami-Dade College has multiple sites, multiple campuses, and they're all interconnected together. But that's the campus area network, and the campus area network at some point connects to the wide area network, which is the rest of the county, right? You can also have a PAN, a personal area network, which is just what you have at home. That's your, or any little connection you can have. Other terms which you might hear is the buddy area network. Well, yes, I I think I don't know if it's coming up or fading out, but haven't heard of band too much. SAN, of course, yes, the storage and a network. Those are very popular because you might have a storage network, and then your wireless LAN. That is a separate LAN from your wired than on your wireless network. Wireless network, of course, where all your devices connect through radio waves, right? That's considered another LAN in your home. So in your home, you might have you'll have two LANs. You have your wired LAN where the computers are connected directly to your router, and the wireless LAN that it's on your wireless network. And those two connect, of course, to your little home small office router, and that router makes the communication between the two LANs, the wireless LAN and the wire LAN. And here you have more of a somewhat larger description of a network where you have a router in San Francisco that connects to the LAN A, right? And that LAN A also is cascaded to another switch on a bus topology. Remember, this is star bus topology. It's a bus between the router, the switch on top, and the switch at the bottom for LAN A. And then all your clients connect to your switch through their local network cards, right? And on the right-hand side, you have LAN B for Philadelphia. And similar setup, you got two switches there in a bus. And all the clients are connected to the individual switches. Like I said, those could be two separate departments. They could be two separate LANs also. And then everything is aggregated by the one router that connects to the other router and through the one connection. Now, at home, or in a small office network, you might see something physically like you see on either side, but the connection that you see here on the one, that's more a logical connection because you don't have a a straight cable, connecting San Francisco with Philadelphia. That doesn't happen. It is no straight connection like that. So that's more that line there on the one is more of a logical connection, which San Francisco will connect with its own provider, and Philadelphia will provide with a local provider there in their city, and then those two providers will use other providers in able to through the internet to be able to find that connection and make that one connection across. So that's here we have some physical topology with a logical topology in the middle. All right, so now we jump into the meaty part of this chapter, which is the 7-layer OSI model. The book makes this analogy, which is a really good analogy, that how you go through multiple steps in order to have communication between a browser and a web browser. In this case, the browser is your Mozilla or your Edge browser on your home computer, and you're trying to reach a web browser um, somewhere on the internet. So that information goes into your operating system. It goes to your hardware. The hardware goes into your cable or your connection, and then it kind of follows the same steps backwards, through the hardware to the operating system all the way to the web server. So that's sort of how the OSI model works. Like I said, is a protocol. As a protocol, it has these rules, and we'll get into those, which is very important rules. All right, so this is the OSI model, 7 layers. If you see on the left, you got layer 1 is your physical layer, 2 data link layer, 3 network layer, the 4 your transport layer, 5 is your session layer, 6 your presentation, and your 7 is your application layer. So 7 layers. Now, if you see the color coded in there, layer 1 and 2 is specifically for the hardware. Physical layer 1 is your wire, and layer 2 is your NIC on your computer, your network card. And then you go into layer 3 and 4, which is more where your TCP and IP happens, right? TCP and IP is just a control on the NOS. And then the other layers, 5, 6, and 7, deal more with how this communication happens with the TCP/IP protocols for HTTP, HTTPS, and all that. And then your layer 7 is your application layer. That's where your actual software, your email client software, or your web browser client, or any other client that you use in your application runs on the layer 7. So it's 1 through 7. I will go through every single one of them so you can get a little bit understanding of what role each one of them plays in the communication. So the book starts with layer 7. It starts from the top to bottom. So layer 7 is where your application layer goes. That's your software itself, right? Your web browser, your mail application, anything that you have, and this is where your payload happens. This is where your information that you're sending or that you're receiving, is being handled. That's called the payload, and that's the actual information that the operating system is going to use to send through that application. If I am uploading a file, then that file is my payload. Now, layer 6 is still part of that software layer. So layer 6 is your presentation. So in here is where things are being reformatted to compress it, to encrypt the data, right? So this thing, it's important to remember, that encryption. This is what encryption happens on your layer 6. But like I said, here it gets compressed or encrypted to send into your message. And let's continue. Now, layer 5 is your session layer. Session layer is the one that establishes that session between your sender and your receiver. That's the one that actually gets like a handshake to make that a connection between the two. This is where the connection gets established and it gets tear down. So this is where the operating system use an API, an application program interface, to handle that connection, disconnection of that uh, communication between the two clients. All right, so layer 5 sends that information to the layer 4. Everything is a step down, right? It goes through all the layers. So now let's recap. Layer 7 was your application, right? And that's where your payload is. So it goes to your layer 6, which is your presentation layer, and then it goes into your session layer, where the things will get more either encrypted or compressed, and if that payload is now presented in a encrypted way or compressed way, and now it sends it to layer 4. The layer 4, that's where us people that work with networking are really come into place. This is where it starts making more sense for the network. When this information is actually really important for us, where we take it, and from here the network is the one that takes that. So here's where you have two ways to send that information. This is the transport. So the transport layer is the one that's going to decide how that information is going to get transported from one place to your endpoint, to your end location where you want to send this to or receive it from. And here there's two protocols, your TCP, Transmission Control Protocol, or UDP, User Diagram Protocol. Difference between the two is that TCP is what is called a connection-oriented protocol. Connection-oriented protocol creates a link between the sender and the receiver and expects to do communication between the two. It's like if I can set a hello and I expecting to receive something in return to say, oh, hello, I'm here. It's like when you pick up a phone and you call somebody, the other person answer the phone, right? You initiate the connection, the other person answer the phone. Most likely he will say hello. Now, when you get that confirmation someone picked up the phone, you go, oh, hello, this is Juan. So now you're introducing yourself into the communication. The other person said, okay, Juan, who do you want to talk to? So now you start establishing that two-way communication. That's what TCP does. TCP is a connection-oriented protocol where it will establish a connection between the two, and like I said, it transfers communication between the two, and they agree in many other things that they need to agree with in order to make that communication, right? If I call somebody and I don't announce myself, they go, oh, who are you? Who do you want to talk to? Then the other person is not going to know how to handle my call, right? So TCP is a way to handle that. It's like it's part of the protocol. UDP, on the other hand, it's called connectionless protocol. Connection protocol, all they do is deliver messages. That's it. Or receive messages. And that's it. I can just pick up the call, dial somewhere, and I said, hey, the store is open. And that's it. Am I waiting someone to say, hey, but at what time do you close? No, nothing. I just say, I'm open. Or I can pick up and say, do an announcement that said, hey, the store is closed. I'm not saying everybody, it's not saying everybody leave. You need to get out of the store in the next 5 minutes because we're closing the register, blah, 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 blah. Do I expect a call back, or do I expect someone to answer back to me? No. I'm going through the PA system, announce it, and that's it. I deliver a message. Now, if you're on the other end, you receive that UDP message. You're a client or a customer on the store, and you hear someone on the speakers going, the store is closing in 5 minutes. Are you supposed to reply back and say, oh, yes, I hear you? No. You receive that UDP message, you take it, you analyze it, you do whatever you want to do with that message, but that's it. You don't reply back to that sender. So that's the difference between UDP and TCP. TCP expect a communication back and forth, some kind of handshake, some kind of communication between the two in order to establish a meaningful communication. And TCP, connectionless protocol, that will just deliver messages, either deliver messages or receive a message. Like I said, if I send a UDP, someone's going to receive that UDP. So I'm the sender saying, store is closing in 5 minutes. I'm the sender. Do I care who received it? No. Do I care if there's 20 people in the store, 100 people, or just one person in the store? No. Now, if I'm on the floor, I'm just one person there, and I receive that message, do I care if others around me received it? No. All I want is for me to receive it. And when I receive it, then I get that information and I process the information. It's like, ooh, I got to leave within 5 minutes because they're closing the store, right? Nothing else to say, nothing else to reply or anything. So anyway, so all of this is handled on the layer 4. And that layer 4 creates a header, right? And that it puts the information there to tell you if the message is TCP or UDP. So on that header is embedded there to say, hey, where you know what kind of communication you're going to have, right? And also, this is where encapsulation happens. The message is being encapsulated on a um, information message is called a segment, right? If it's a UDP, it's called datagram. But if it's TCP, it's called segments. But for the most part, we call segments. And also, interesting is that on the transport layer, that's where you define which port number you want to use. Remember those TCP ports that we saw before, 80, 443, 21, da da da. That's where all that information gets in here. When I get that information from the application layer, I said, oh, that was a web browser. So let me see that this payload, is the payload encrypted? No. Okay, so I'm going to use port 80. But is it encrypted? Yes. Well, I'm going to use port 443 because that's what 443 uses. All that information gets embedded on this layer 4. To see how now the information starts to get more a little complicated, because now it's not just your payload, it's also it's a TCP, it's a UDP, what port you want to go to, and now it's being encapsulated in what's called a segment. And that gets delivered to what? Layer 3. So here's layer 3. Layer 3 now receives that layer 4 information, right? And this is the IP layer. This is where the IP information resides. On the layer 3, that's where you will see IP addresses. Now, on this layer, the information is encapsulated again, what is called a packet, right? So that segment is now put into a packet with another header, with the IP header, and this IP header will have now the IP addresses, the Internet Protocol addresses that identifies who is the sender and what is the destination that you're going to. IP addresses, we'll get more into that later on, but IP address is a specific set of numbers that identifies who you are on the internet. Everything on the internet is by numbers, right? Everything goes by IP numbers. It's kind of like your phone number, right? It doesn't matter what your name is. You always will get identified by your phone number, not your name. You can have, there's a lot of people with the same name, especially Juan Sanchez. There are many people with that name. So, but I have a unique number, and that number belongs to me, and that's the number that people use to call me, or for me to call somebody, identify myself, that's my number, right? So IP address is similar. Is similar to this. That you get an IP address assigned to you, and that IP address for the communication they use in a specific location, you get that IP address, and that's the IP address identifies your computer and your communication. So all that gets embedded into this package, right? And then here is where you have what's called the ICMP and the ARP, but we'll get into that. But ICMP is more is for internet control, and the ARP is for the address resolution protocols, which is also, so we get more into that. But here is where large packets can be divided into fragments, so you get fragmented. So when sometimes I don't know if you heard or seen um, on troubleshooting that it says, oh, you're getting packet losses. Well, if you're getting packet losses, it's at a layer 3. That's where packets reside. And when you said, oh, your information is being fragmented, or you're losing fragments, well, it's at this layer, the layer 3. Now, everything gets embedded now, furthermore, into the layer 2. Now, the layer 2 is the last meaningful layer of the OSI layer, OSI model, and the data link layer. Here's where you interface with your physical network card, right? With the physical network card of your computer. Here, the information is embedded into a packet called frame. So this is where you have your frames. And here's where the MAC addresses reside. A MAC address is the media access control address. Now, each device, each network card has what's called a MAC address embedded in it. That is a unique number worldwide that is unique for that one network card. That's how the only way that anybody can identify where you're coming from or what computer you're using, because this MAC address is embedded on every single machine. It is a unique number. There's not supposed to be a duplicate MAC address in the world. There's plenty of numbers. Companies are allocated a range of numbers when they create when they make the NIC cards. On each NIC card, the network interface card, not the device, not your phone, not your computer itself. Your network card is the one that gets a MAC address. Your phone gets assigned a MAC address. Now, Apple on some of the devices being smart, where they can actually can generate multiple different MAC addresses for your phone. So every time you connect to a network, you can be seen as a different client, not the same one you had before, which creates some problems for security and some other things. That's a different story. But that MAC address is supposed to be unique. But some devices are now not obeying that rule. But anyway, data link layer is the now is the physical interface that connects you to that one wire connection. So the next layer is that wire. So here, layer one is the physical layer. That's what it connects you to the network. Doesn't have to be specifically with a wire. If you're using fiber optics, it's a light, right? If you're using wireless, it's the your radio signals. That's your layer one for wireless. That's the difference between a wire connection and wireless connection is on the layer one. Everything else obeys all the rules, right? But on somewhat a little different settings, but your layers is still all the same. But on layer one, your physical layer is the one that changes, because yeah, it's not a wire anymore. So they're not electrical pulses over a copper wire. It's a radio communication, radio waves going through the air. So the air is your medium, or it could be wavelengths of different fiber optics when you throw the light over fiber. So that's your layer one. All right, so on all those layers, the protocol data units are that information that is embedded on those layers. So let me start from the bottom up. So on layer one, the physical layer, of course, that's your transmission over the, let's say, a wire. So here you have your bits, right? Your bits is just ones and zeros over that communication there. So your PDUs, your protocol data unit at the layer one is just bits. The layer two, which is your data link layer, those are called frames, and that's like a layer two PDUs. A layer three, it's packets, and layer four is segments. Like I said before, on networking, we are really mostly interested on this 1, 2, 3, and 4 layers. That's where we troubleshoot, that's where you work with, and that's where we control the data through this 4 layers. Now 5, 6, and 7, yes, they're important because that's where the payload is. That's your layer 7 PDU, and is the one that do your presentation, you do your session, your encryption. You need to do encryption, and that's how you present it to the users on your layer 7. But this is your data, your payload. Now, one thing that I do to remember this is, since I care only about 4, 3, and 2, and then layer 1 of my bits, you see that segment packets and frames. I always remember, my trick is remember your sunscreen, right? Your sunscreen is rated on SPF. SPF 40, SPF 20, SPF 100, whatever. So if you remember that, you'll see that it's segments, S packets, and frame, SPF. Just keep that in mind. I will help you remember when you're talking about this is segment, packets, and frames. And then you got bits. Just layer 1 is just bits. But that will help you remember when you hear the word or the frame, packets, and segments, because you will see when you have segmentation, when you got packet losses or you got frame losses, then when someone tells you, oh, no, we're getting packet losses, you're like, oh, layer 3. Or you're getting frame problems or frame losses. Okay, that's layer 2. So, and then if you get bits losses, or there'll be your layer 1. Your problem will be much larger if you start losing bits on a layer 1. But keep in mind those segment packets and frames. and here's more like an overall view of summary of this encapsulation. So you got your application layer, send it everything to your presentation layer. It goes to your layer 5 for your session to create that session, right? And that's your payload. Now, when it goes into the transport layer, you see that you have on blue, you got a header, right? That's the header for your segment. And then when it goes to layer 3, you get another header to identify your packet. And that header there, it is going to encapsulate everything that was above. And then when you go to your data link layer, your layer 2, this you get a header and you get a trailer. Why is a trailer? Because that's how you're going to close the frame. That says there's no more information here. There's no more else to add to this. And it goes now with a header and a trailer. So it identifies beginning and end. And it goes into your physical layer on your wire and gets across the network. Now, when it goes to a switch, the switch is a layer 2 device. Switches don't know IPs. Switches don't know network. So all they do know is data link. And that's where switches identify all the clients through MAC addresses. Because remember that MAC addresses reside on the data link layer, right? So it will identify the MAC address. It will set that embedded packet there, with the header and the trailer, and then forward it to a router. Now routers, they do work on layer 3. Routers are layer 3 devices. And layer 3 devices are capable of going into that information, unpack it, right? Look at the layer 2, unpack it to the layer 3. Now he's going to look at that header. He needs to look at that header in order to route the traffic correctly, and that will send out to the internet to whichever endpoint is going to be, and that location is going to reverse this again and deliver that information to the web server in this case. Now, let me give you an example which might help you understand this. I'm sending a letter from Miami to New York, right? I write my information on a piece of paper, right? The old-fashioned way. I write the letter or print it. Yeah. And then that's my payload. That's my information, right? If I decided to encrypt it or not encrypt it or compress it, that's out of different way to write your document. Whatever you want to write, you write it, and that's your payload. So that payload is going to now hand it off to the transport layer. So the transport layer is when I actually take that letter, close it, and put it into an envelope. So that header that you see there, that has the payload inside, imagine is your envelope with your letter inside. Now, what is that letter going to do inside the envelope? It's protected, it's sealed, nobody's going to see it, and it's already on a, in this case, it's a segment, right? So now it goes to the network layer. On the network layer, I put another header within that envelope, right? So this header, let's say, is your addresses for the sender and the receiver. Said, okay, I'm sending from Juan Sanchez at Miami-Dade College, Miami, Florida, and I'm going to send it to blah, 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 and in New York, I don't know, 100 Main Street, New York City, New York, right? So now I'm adding more information into that. And then I go into data link layer where it's actually packed. So when pack it in this way, we keep talking about the letter. Now I have a letter with a sender and receiver. So I'm going to hand that off to my mail carrier, right? That's my data link layer. He's going to be my carrier. He's going to take a look at that. And he's going to say, okay, this is a letter that he's going to go into basically the layer 2, and he says, okay, this is going out of Miami. Here's the switch. He's going to look at that. He goes, okay, this is going out of Miami, and he gets send this to the central office in Miami. So the central office in Miami gets this, looks at the all the letters they received that day. They looked at my letter and they unpack it all the way to the layer 3, which is where I put my sender and my receiver addresses. Because now the router is capable of seeing IP addresses. So that header will have the sender and receiver. So he's going to get that. He goes, oh, at least this letter goes to New York. So I'm going to route it to New York. And he will send it off to, I don't know, he will put it into a big bin that goes to New York, send it to the airport. The airport will see that and say, okay, this has to go to New York. The airport will get that, send it all the way to New York. Then you receive it there. He goes, oh, this is letter going to 100 Main Street, so let me deliver it to the router there that handles a mail delivery to the 100, Main Street in New York, and he's going to receive it there. Now, do they need to see what's inside the letter? Do they need to open that letter and see the content? No, they don't. All they do as a router is to route the traffic where it's supposed to go. If that letter is going to California, he will not send it to the transport that is going to take that to California. He will make sure that is actually the one going to New York, right? So he has to route it correctly, because if it gets routed incorrectly and it gets to California, California is going to see it. It's going to again open it up to look at the envelope. Goes, this is not for here. I gotta send it to New York. That's when you get traffic delays. That it gets sent to the wrong place, and that place, if it's right, he will see it. Go, that's not for me. Let me send it to New York, and he will get it there. And in there, it goes now the opposite way, right? It gets delivered to the mail carrier with a big pack that he goes, hey, mail carrier, you're the one that go to Main Street, so go and deliver this. He's going to look at that packet information and then go all the way up the stack, layer 4, layer 5, layer 6, layer 7, and deliver that information to whoever gets that. Whoever gets that letter is going to open it at a session layer, the layer 5, and then if it's encrypted, he will decrypt it, and then he will go into the presentation layer to present it correctly, and then give it to the application. The application can read it. So they reverse that information there. When they reply back, the whole process starts again for the communication to come across. Now, the point I want to make here is that if I deliver a letter to the airport, do they care what's in there? Do they care who does it go to where from, or anything? Nothing. All they do, they're movers. So some of the routers are just movers. All they do is move information from one place to another. They're transient routers. The transient router goes, oh, all this traffic needs to go to New York. All this traffic needs to go to California. So all these letters, all these packages, they are just transport. So a lot of those routers in the middle of the internet are just transport. They just make sure that everything gets delivered to the right place. The only one that can open that is when it gets to the destination, right? When you deliver it to New York and it goes to your city, and it goes 100 Main Street. So there's 3 destinations there. It has to be delivered to New York, not just the state, but also to the city. And when it gets delivered to the city, they have to see where in the city it needs to get delivered. So they need to get that information. Nobody else. They're the only ones that need to get that information. So that's how in the internet goes. So that's why you have all those headers, and you have all that encapsulation for your segments, for your packets, and for your frames, because each portion of the protocol that needs to handle that communication needs to read up to that information. Now, like I said, if you go to the airport, do they care what's inside? No, they don't. They don't need to open it all the way to layer 7. So in this example, that's why you see that from the browser gets encapsulated, it goes to the switch will open it to layer 2, because switch are layer 2 devices, right? And then it goes to the router opens it to layer 3, because those are layer 3 devices, and then he would handle traffic to see where it goes to the web server. And then once he gets to the web server, he's the one that actually cares what's in the payload, and he will open it there. Okay. Now, there's a lot more to talk about the OSI model, and we'll cover more of that in class. But I just wanted to get at least the start from what the book says, and then I can elaborate more when we are in the class. Because now the book shifts us to some of the safety policies, and just to protect devices, and some of the best practices for safety. So in emergency procedures, you should have some kind of emergency a protocol in place for your alert system, for your fire extinguishers, for emergency power off switch, or anything like that. There's some things that you should be aware of. Some of the terms, like when it says fail open, to allow systems to be accessed, or deny when you have a fail close. So if you think about this, when there is a fire, you want to fail open, right? You want to fail open because you want to open all the doors, you want to open all the access doors so people can actually leave. It's a fire, so you need to do fail open. Now, if it's a bank robbery, you do fail close, because now you want to protect your area. You want to protect what is in there. So when there's a failure, and you do a fail close, that's to keep everything inside and not let anything go out. So, for example, yeah, bank robbery, yeah, you will do a fail close. You will not do a fail open. You don't want everybody to get out. So that's the difference between the failure for the fail open and fail close. It depends on the situation. It depends on what the emergency is. You want to fail open or fail close. If it's a I already said a fire. Um, if there's a hurricane coming, you want to fail close. You want to make sure that you close everything, you protect yourself, so nothing gets out, and you protect everything inside. Now, a lot of the equipment will have what's called a safety data sheet. The SDS is the safety data sheet will have just information how to handle substances, how to handle chemicals, what to do in case of an emergency, for first aid, firefighting measures. A lot of places do have fire extinguishing control, so it depends on the chemicals that they have, it depends on the procedures that they have. They will have a different safety data sheets that will show you how to proceed on any emergency. And also, many of us have probably heard of the OSHA, right? The OSHA is the Occupational Safety and Health Administration. They set up all the rules and regulations on how you handle things, or how to handle some of the problems, and what things people can do, people cannot do. That's where they say that um, that you have to wear your personal protective equipment, when you have to ground yourself, how to use the tools properly, how not to use them. It's mostly safety. A lot of places that you have to wear a hard hat. Construction areas, well, that's OSHA that actually requires for you to have that. Just to or to you always use the right procedures when you're using in any tools, just to make sure they're using it the way it's supposed to be, is meant to use, and not use it for something that in a way that is not according to the application that the manufacturer intended for. So OSHA controls all of that. Oh, and one of those is also when you're picking up some weight and you have to bend your knees and stuff like that. All that is recommendations done by OSHA. So here's instructions how to, lifting heavy weights, that you have to see that how the load is handled, right? And you stand close to the object, feet apart, your back straight, bend your knees, grip the load correctly, and you lift it with your legs and your arms and shoulders, not with your back or your stomach, because that's where you can create back problems or hernias or anything like that. So just to protect yourself. You keep your load close to your body. Why do we see this on this networking? Yeah, because you might see some switches that are small, but I have come across routers and switches, especially enterprise routers, that those devices can go over 100 pounds. And some of them are super, super heavy. Even though you remove equipment from the inside, make it lighter as much as you can, it's still heavy. Some of the servers are also in the range of 50, 60, 70 pounds, that for one person, if you don't hold it right, that you don't grab it correctly, you might hurt your back. I have in the past grabbed it, not being careful the way I do it, and then you end up hurting your arms or your shoulders, or just by not picking up things the right way. But it just to be safe. Like I said, we from time to time get to carry equipment that is heavy, so you got to be careful, either ask for help or be carried by more than one person, or have the right equipment. You're not going to carry a heavy equipment across the floor when you can have a cart and put it in a cart and just wheel it over, and then you pick it up and put it where you need to put it. So just to be more practical when it comes to things like that, and be safe. Now, static electricity, it is a problem. It's a big problem when it comes to electronic equipment. Electronic equipment, especially computers, they work on 5 volts and 12 volts. So it's a low voltage. And you know that electrostatic can become thousands of volts in one shock. they have low current, and that's why it doesn't kill you, because electrostatic is a high charge, but it doesn't carry that much current, but the high voltage can actually damage equipment, and it does. In Florida, we don't have that much problem because of the humidity, that we have a high humidity, but if you go to another areas where they have low humidities, then you'll build up more electrostatic charge, and you can damage some equipment. Here, the air conditioning is a device kit that also takes humidity out of the air, so it makes the air dry. By making it dry, it makes it colder, but by being dry, then you can build up some electrostatic charge in your body. So you have to make sure that you ground equipment, that everything is grounded correctly. Remember that third prong on an outlet. The third one, the round one, is your ground. Don't you ever cut that one off. It's for safety. It's needed there, especially you'll see those on larger equipment, most likely equipment that has a motor. You'll see that grounding wire, and that's for safety. If something happens inside that piece of equipment, is built in a way that it will send the discharge through that grounding wire. If you cut it, what happens is it doesn't have anywhere to go, and it will go back to the electronics and fry the electronics. So electrostatic can do two things: can do a catastrophic failure, which destroys everything, or an upside failure, which actually it damages the equipment in a way that is still working, but it will shorten the life of the equipment. Or some computer equipment, electrostatic charge might send the wrong pulse and the wrong equipment and get things out of sequence, or get things out of kind of an upset failure, that things are not working correctly because they're like out of sync, and they don't respond correctly. And sometimes things like that, on an upset failure, you have to disconnect it, reinitiate it, so everything starts to come up the correct way. And that's because just the electrostatic got in there, and it messed up the something with the electronics. So some ways to prevent that is using an ESD strap, right? The ESD strap is just is like a little strap that goes either on your wrist, that has a metal plate that touches your skin, and you can ground that in any cabinet that has grounding. For the network equipment, for us, is really important to have proper grounding, because the switches do require grounding, and you might see that some of the enterprise switches will have in the back an actual connection for a grounding wire. And whatever you install those, you want to make sure that that grounding is connected correctly to either the frame or the cabinet where you install the equipment, and make sure that that frame is actually grounded to the proper building grounding. FPL in our town provides grounding on every location. Even at your home, I don't know if you have seen. If you have a home, you might see in the back, close to your meter, a rod that is on the ground, and you see a wire connected to that, and throughout your house, you'll get all that grounding is connected through that connection that will actually send it to the ground, to that rod that goes to the ground. I believe those rods are about 5 feet long. Even though you see only a few inches sticking out, those rods are 5 feet long, and they go, grounded into the ground. The earth ground, that's the reference point for everything, all the electronics. Remember, the earth is magnetic, and the ground it's the neutral point of electronics. So that's why you need to have that. But it is important to make sure that you ground yourself, and when you work on equipment, make sure you shut down the equipment and unplug it before you work in it, just in case you don't get shocked or anything like that. But it's better to always shut it down and unplug it. But grounding is important. We had, actually not we, but FIU, Florida International University, at one point they had some problems with some of the access points that they had. They will get fried all the time, some of the wireless access points, and that was because the connections that they had, the pipes that they had to get the wires across to connect to the network, they were plastic, and that would not provide proper grounding, because here at the college what we do is that we do it with metal pipes, and then those pipes are actually grounded. So whenever there was a lightning hit or something, the access point would absorb all that electricity, static electricity, and it would have fried the electronics. But that was at FIU. at the college, since we use metal pipes, then it would actually send that grounding through that pipe, and they will stand any lightning or anything like that. So it is important. It's really, really, really important. Actually, AT&T will not provide equipment to a business if you don't provide a proper ground, and they will make sure that that ground is connected to the building ground that's connected to the power provider ground. If you don't provide that proper grounding, they will not install any of their equipment. They want everything grounded, and they're right, because if they don't have it, chances are any lightning or any problems, it will fry their equipment. Now, later on the book, we'll go more into troubleshooting network problems, but here the book's trying to give you like a little heads up on troubleshooting. But like any other troubleshooting, you want to identify the problem, see the symptoms, see what's going on, what do you see that is not working correctly, and then you establish a theory or probable cause of what is causing the problem, what could be affecting this procedures that not to complete correctly, and then you test your theory to determine the cause, and then establish a plan to resolve that problem and implement that solution or escalate the problem. If it is out of your hands, has to go to another area, so you escalate that problem. So once you implement or it gets escalated, so somebody else to implement the solution, you verify that it is working, and implement the preventive measures so it doesn't happen again, and then you document the findings, your actions, and your outcomes. And for every problem, there should be documentation of how the problem got resolved, so next time you experience that, they know how to proceed to set up a procedure how to solve the problem. Or if you can prevent it, then you can have documentation that says, okay, this is the way that we thought they could be prevented. If it happens again, that means that of course that prevention didn't work right, so it has to be readjusted. So it's an ongoing process, right? So you identify it, you see, kind of guess what's happening, do a theory of how you can solve this problem, do a plan, implement it, see if it works. If it does, then document it. And I think that's the end of the chapter. And yes, yeah, that's the end of the chapter. So we'll go back and we'll start going more and more into the OSI model. Like I said, this is very, very important. There is a video that I also put on Blackboard that it talks about the OSI model and how it's explained. And this is, out of this whole chapter, that's the most important thing they need to remember and to learn on how the TCP IP stack works. Everything has to do with all the layers, your MAC addresses, your IP addresses, your TCP IP ports, your TCP, UDP, all of that is really, really important to know, because those are the building blocks of how networking works. And on everything, if you know how it works, you can troubleshoot it. If you don't know how something works, it becomes very difficult for you to try to establish what the problem is if you don't know what's the procedure, how things actually, that protocol works, what is it that the protocol requires for how things are supposed to happen step by step. For something to work. When you don't know those steps, it makes it very difficult to be able to troubleshoot something. So we'll go back to cover more of this in class, and you're welcome to bring all your questions or anything that you see you hear here, and we'll discuss it even further there and show you some examples on it. Okay, thank you for listening, and see you in the next chapter.